What is electric current? Under what conditions does it occur? In our video, using 3D animation, we'll try to figure this out. In today's world, it's hard to even imagine how we could live without electricity. It's all around us. We use electricity in our daily lives. Electricity allows us to light and heat our homes, use various tools and household appliances, perform medical procedures, travel by various modes of transportation, and much more. When evening comes, we use electric lighting. There are many sources of electricity today. Most likely, no one can tell you what electric current looks like. There are many theories about what a flow, or lack thereof, of electricity looks like. In an old, widely held theory, electric current is compared to the flow of water through pipes. There's a theory that current travels through wires in the same way that balls transfer energy to each other when they collide. And there are other theories as well. But, after all, electric current does exist, and we're all witnesses to it. In our case, we will consider electric current produced by a generator. So, a long time ago, there lived a man named Michael Faraday. One day, out of sheer boredom, he discovered electromagnetic induction. This happened almost 200 years ago. What did he do? Let's take a look at the essence of his discovery. First, let's take a permanent magnet. Let's assume the magnet is elongated. The magnet's cross-section can be any shape, square, round. It doesn't matter. Every magnet has poles. For convenience, they are called the north and south poles. A magnet also has a magnetic field. The lines of force of this field run from south to north, inside the magnet, and from north to south on the outside. Place the magnet vertically, with either pole facing up. Now take a ring made of any conductive metal, such as copper. Place the ring on top of the magnet and let go. The ring will slide down smoothly and slowly. Could this be some kind of coincidence? Let's try doing exactly the same thing with a ring made of a different material, such as plastic. The plastic ring falls freely. Let's try the copper ring again. Once again, it slowly slides down. Now let's make a slit in the copper ring and let it slide down along the magnet again. Now the copper ring falls freely. What's the secret here? Electromagnetic induction. An induction current is generated in the non-ferrous metal ring as it falls along the magnet. According to Lenz's law, the induction current generated in a closed circuit always flows in such a direction that the magnetic field it creates opposes the change in the external magnetic field. It turns out that the magnetic field lines generated in the ring are directed in the opposite direction from the magnetic field lines of the magnet. And since the cut ring does not have a closed electrical circuit, no induced current is generated in it. No current, no magnetism. Therefore, the cut ring falls freely. Why doesn't the ring, which isn't cut, stop and remain suspended in place? Because motion is necessary for an induced current and the magnetic field it creates to occur. An induced current arises only when the ring crosses the magnet's lines of force, and the ring slowly slides down along the magnet. Now let's wind the electrical wire into a coil and connect the ends of the wire to an ammeter. And let's move the magnet inside the coil. As the coil moves, electromagnetic induction occurs in the coil. The ammeter needle deflects, indicating that a current is flowing. The current flows in one direction. The magnetic flux increases. This continues until the coil reaches the center. At the center, the current instantly drops to zero. The magnetic flux reaches its maximum value and ceases for an instant. After passing through the center, the current reverses direction and the magnetic flux begins to decrease. The ammeter needle deflects in the opposite direction. Why does this happen? According to Lenz's law, the coil attempts to maintain the equilibrium of the magnetic field and opposes the magnet. It tries to push the magnet back with its own generated field. And when the magnet passes through the center of the coil tries to hold it in place by reversing the magnetic flux. The coil's magnetic poles change. Accordingly, the direction of the current changes as well. This coil is quite temperamental. It doesn't like it when the magnet enters, and it's unhappy again when it exits. If you move the magnet in the opposite direction, then all the changes in the directions of the fields and the current will occur in reverse order. The direction of the electric current in the coil can be easily determined using the right-hand rule. Wrap the palm of your right hand around the coil so that your thumb points toward the north pole of the solenoid. Your four bent fingers will indicate the direction of the current in the coil's turns from positive to negative. If you try moving a magnet outside the coil up and down, the same processes will occur. And if you move a magnet standing vertically in a horizontal plane, you will see the same result. Now here's something interesting. If you rotate the magnet 90 degrees, lay it on its side, and in this position, move the magnet over the solenoid. The magnet approaches. The solenoid at the top generates a pole of the same name as the magnet's nearest pole. The current increases. The ammeter needle deflects. At the center, the magnetic flux is at its maximum and instantly drops to zero. What will happen next? Will there be a change or no change in the polarity and current in the coil? Let's leave this question open. I hope viewers will write in the comments what they think will happen. If we move the magnet inside the coil again and start increasing its speed, then the generated current will increase. The meter's needle will deflect more strongly. And if we move the coil while the magnet remains stationary, the coil will still generate a magnetic field and an electric current. The coil began to move upward from the center of the magnet. At the start of its path, the magnetic and electric flux in the coil are at their maximum. The coil's poles are oriented so that the coil is attracted to the magnet. The coil moves away. The magnetic flux decreases until it disappears completely. As it moves downward, the coil generates a magnetic flux that causes it to be repelled by the magnet. The magnetic flux in the coil increases and reaches a maximum at the center of the magnet's field. As it passes through the center of the magnet, the coil's magnetic flux disappears for an instant. It is zero. Next, the coil begins to move away from the center of the magnet. The current reverses direction. The magnetic flux begins to decrease. The coil generates a magnetic flux that causes it to be attracted to the magnet. So, we now know that an electric current in a closed conductive loop arises when either the loop moves through a magnetic field or the magnetic field moves through the loop. Based on everything we've discussed so far, let's try to build an electric current generator. We already know how electric current is generated. Let's modify the solenoid slightly. Let's add 2 metal rings to the solenoid. And let's add current collecting brushes to the rings. The generated current will flow through the rings and the brushes. Let's add magnets on either side of the solenoid. The magnetic flux from the magnets is directed in one direction, from south to north. South is red, north is blue. The poles of both magnets alternate and are directed in the same direction. Let's start rotating the solenoid. The solenoid will immediately begin to generate an electric current. The fields generated by the solenoid will be opposite to those of the magnets it is approaching. The direction of the current will follow the right-hand rule. The magnetic flux and electric current in the solenoid will increase until it has rotated 90 degrees. During this phase of rotation, the magnetic flux and electric current are at their maximum. After this phase of rotation has passed, the current will begin to decrease. In this phase, the magnetic fields and electric current in the coil do not reverse, as they did in our previous experiments. Why? In past experiments, both the coil and the magnet moved in such a way that their geometric centers shifted relative to each other. Therefore, the polarity and the current changed. But now the centers of the coils or the magnetic fields remain in place. Therefore, the current and the poles in the coil do not change. However, there is rotation and the magnetic fields intersect with the turns of the coil. Therefore, there is also electromagnetic induction. The current will decrease until the coil has rotated 180 degrees. At this point, the current drops to zero, and the polarity and direction of the current in the coil change. The polarity change occurs because the edges of the coil begin to approach the now opposite poles of the magnets. The coil will generate fields to counteract the rotation. It will always resist motion and rotation. In the phase from 180 to 270 degrees, the current rises to its maximum, but with the opposite polarity. And from there on, everything is clear. If, for example, a steel rod, core, is inserted into the solenoid, current generation will be significantly more efficient. The magnetic flux will increase, and the current will be stronger. The steel core and the rotational speed have a key influence on the strength of the generated current. This is the principle behind how an AC generator works. Here's an interesting point. It's possible to configure the system to generate direct current. To do this, you need to make some changes to the solenoid's design. One of the commutator rings must be removed. Connect both solenoid terminals to the single remaining ring. The second ring must be cut into 2 parts so that when the polarity in the solenoid changes, the current collecting brushes switch contact from one half ring to the other. Now let's see what happens when the solenoid rotates. When the solenoid rotates, everything happens just as we discussed earlier. The direction of the current is shown in the video. When the polarity and current in the coil change, at that very moment the contacts of the current collecting brushes switch from one half of the rings to the other. The current flows through the brushes again in the same direction. In this video, we examine the basic principle behind how a generator works. The nature of electromagnetic induction and electric current. Now we know how electric current is generated in a closed conductive circuit and how a generator works.